Thank you all for coming today. Printed circuit boards, short PCBs, are essential to modern computing, and Kitty will tell us a bit about them today. Take it away.
Yeah, thank you. And thankfully, this talk is not about color-accurate photo editing. I swear night shift is off, but somehow we have a bit of a yellow tint here. But yeah, I guess we're going to deal with that. So, yeah, I want to talk about PCB design and more specifically how I transitioned from like the more typical PCB design approach when it comes to designing schematics to writing schematics with code. So, and also like the reasons why you would want to do that and the current state of that project that I have been working on. A little bit about me, you can call me Kitty. I consider myself like a designer, come originally more like from product design, web design. Also started tinkering with a lot of projects, got really much into LEDs, building LED projects, and spent a lot of time at tech spaces and love to learn new things and share my knowledge that I learned with others. And one of the things I come across was, well, PCB design after designing a bunch of LED projects and wanting to go the next step in being more creative in terms of what I can build with LEDs. A bit of a summary though, like for those who are not familiar yet with like how you actually design a circuit board, like the boards that, you know, is this in like all your smartphones, laptops, and every electronic device. You typically have like a software like KiCad, for example, where you design the PCB from schematic, which is like this theoretical overview of like what components do you have, what pins do they have, how are they connected with each other. You really do not care at this point how the parts look like, where they're positioned on the board, and all that stuff. It's just about how they're like connected, generally speaking. KiCad is one of the most commonly used software since it's like also open source and has a huge community. And quite honestly, it's also one of the few open source software with a graphical user interface that is decently usable from my perspective. Should be more of that. And yeah, so that's like typically the first step, and it's done with this visual overview. You see these kind of schematics a lot in data sheets that try to help you to understand visually how things are connected. And like for simple stuff, that also works perfectly well, and like it's easy-ish to understand. The next step then, once you basically have the schematic design created in a software like KiCad or like some commercial software like Altium, you would then go and actually place the components. Here you then actually see the physical representation of those components, everything from like the buttons, the pin headers, the USB-C ports, and all that stuff. And you place them on the circuit board, and then you figure out how to connect them with copper traces so they're electrically connected and can do the thing that you want them to do. And once that is done, you would then typically export it from KiCad. There's like this so-called format, that's called Gerber files, and those are like then used by the manufacturer to basically then, create the circuit boards layer by layer in the factory. And like in KiCad, you either have the option to just export the whole Gerber files, or you can use plugins that are specifically for specific PCB manufacturers like GLC PCB or PCBWay that help you to directly export the files, including the positioning files of the components, so you can then upload them. And then you would basically upload those zip files, or like that zip file, to like a PCB manufacturer website. For example, GLC PCB or PCBWay or Eisler, to name actually a German one also. And there you then basically have like all kinds of selections of how you can customize the board, what kind of coding it should use, and all that stuff. And then you can order them unassembled and then hand assemble like components on the board, or you can order them assembled with components. So that's like the typical approach: schematic, layout, exporting, ordering. Actually, I forgot one thing, that once you then order the PCBs, you get it delivered after like a week or a few weeks, You back them out, you connect them, you test them, you realize that something doesn't work, you try to figure out what on earth is going on here, eventually you probably find the issue, go back to the schematic, fix the schematic, do the layouting again, export again, ordering again, and because it's so much fun, let's repeat it a few times. Yeah, maybe I'm processing a bit of a trauma here, but learning from that is ideally design your circuit boards in a modular way that instead of directly combining everything together, first, for example, if you have like USB power delivery for getting power, have a separate module for that, test that first, have like one for like power conversion if you need that, and then connect them step by step together instead of having like everything all connected together, because you're probably going to save money, you think, but then you don't because you end up needing to buy more PCB variations. Yeah, it just makes things a lot easier if you separate them all by modules. Coming back to schematics though, what is quote-unquote bad about the typical visual schematic way of editing? I mean, for one, they're like especially if you work with LEDs or like other things that are quite repetitive, like copy pasting LEDs and the capacitors and connecting them over and over and over and over again. Have fun doing that for like 200 LEDs in a row, for example. It takes a bit of a while. Also, I mean, like in data sheets, you have like calculations for like converter, for example, that help you to figure out what like resistor values and capacitor values you need for your certain use case. By the way, is the audio still good? And also, like when you start to work on more complex designs, these schematics tend to get a little bit difficult to actually fully understand at first, and they can get a bit overwhelming. Also, because like Git for like actually making sure that you can go back to like a previous state of your design isn't really well integrated into KiCad. I keep forgetting to actually submit my changes into Git, and then when I do want to go back to a previous state, it's quite a bit of a hassle. And maybe if you have been doing PCB design before, you might have similar experiences like that. So after doing a bunch of like PCB designs with this typical approach, one day while waiting for winter to end in Berlin, I stumbled over this article about this open source project called Atopile, where you can code schematics. And I said, okay, that sounds interesting. And I was checking that out and tried it out myself and actually kind of liked it. So, and this is like the project I'm going to focus on today, but I'm also going to mention some like other projects that maybe some of you have heard about before or later. But yeah, so let's see, how does the process actually change when it comes to creating a schematic with Atopile instead? Like, it's not actually replacing the full PCB design workflow. It's really focusing on the whole schematic. Instead of creating a schematic in this visual overview, you instead create a schematic in the code editor of your choice, for example, Visual Studio Code. And then you export a netlist file, which you then just import into KiCad, and then you just do your regular PCB layouting process. You can also, from KiCad, manually export stuff as usual, or, which is actually kind of cool, you can also use this atto build command to then even, if you want, for example, also create like a PC, to also then add the git hash of the commit, basically of the version that you're like releasing here, and can print it directly on a circuit board automatically, which can also be quite useful later on for identifying what design version was this actually. But besides that, it's basically, we're just going to change the schematic aspect. And since I think it's like better to actually show how that looks like in practice, I'm gonna show you like a simple project. Let's start with a simple project. And so I'm like here in Visual Studio Code, and basically I have a module here. And the nice thing about like having everything like encoded is also that you can split up everything much better. Even like complex systems, you can much better like separate into their parts. And like in this case, I then basically have like this LED, like a WS2812B LED. And I have like basically a power interface that makes it easier then later on to basically connect everything with power, or like define also what voltage it has. And at the top we have like the typical imports that we also are familiar with from like other programming languages. And so here it's just like a very simple project with a bunch of LEDs, and they're connected to power. And I even have like defined what the data voltage of those LEDs are, which can be relevant later on. One of the fun things also that you have here is, so I mentioned like that you have everything like separate into different files and modules. And now I can actually click on the LED and I have like an overview of like how it's built up. So for example, like here I have I only imported this LED, but what you always want to have with this LED specifically, according to the datasheet, is also a capacitor. So I don't need to remember to always also add the capacitor with the right value here, because I have a module where like the actual LED with all its pins is basically placed and then connected with the capacitor, which in this case is like 100 nanofarad. Also, one of the cool features of like Atopile specifically is that while you can define a specific component ID for then automatically, how to put this? So like Atopile currently is like optimized for this workflow to work with KiCad, and then you create your PCB design for ordering on JLC PCB. Even while they do plan also on extending it to like other PCB manufacturers and their component databases. But the nice thing is like the way it currently works is it can automatically search for the component that you need, instead of having to have like a specific idea of a component. So more specifically, I have like a capacitor and it has 100 nanofarad, and it will automatically search then for capacitors with those values. With those values, and then automatically compile everything and export basically the list. So if one component is out of stock, it just chooses a different one with the same values, which is quite useful. So you don't always have to recreate your code basically just because one component is out of stock. And there's also like the long-term idea more to like have more and more components automatically be chosen based on the requirements that you have, instead of saying I need this exact specific component. So yeah, I have like this LED here. I connected it to power, and I told it then also, for example, what voltage it has. And up here we basically have like the ID from like LCSC specifically, so it can automatically then prepare the files for then also ordering them, and like also assembled if you want to. We can also define our own variables, like for example, how much current does it maximum like draw, which is then also going to be quite useful for calculations you can do, and then also to automatically check, or like to let the compiler automatically check if what you're building there is within the specifications of the datasheet. So we have like calculations and assertions like directly integrated into Atopile, which is quite useful. Like for example, we can check if the power that I actually connected to the LED is within the voltage range that it is compatible with. So if by accident you somehow then have 20 volts connected to what is supposed to be 5 volt, the compiler would tell you that you probably don't want to do this, which can save some issues. What else? We can add comments in the top. Like there are a lot of interfaces that make like the whole work a lot easier. For example, there's like an interface specifically for like an interface component for USB-C for USB, for example. So that the idea is that, for example, if you have like a modern ESP32 microcontroller, which has like pins for the data, pins of a USB-C port, you can actually say what pins are those connected with. And later with another component where you also like, let's say you have like an USB-C port, you then don't have to look up anymore like what specific pin was the data plus again of like the microcontroller. You just say USB-C connector.USB is connected to ESP32.USB, and the rest is then automatically connected correctly. And the same applies to like stuff like serial and UART, which makes the whole code base also a lot easier to read, and you don't have to always look up again like what pins are for what purpose, basically. And since we're like in a coding IDE, also one of the fun things that you can do is use Copilot. And so, like, especially when it comes to, easily connecting a bunch of like LEDs, this can save you a lot of time because you don't have to manually do that anymore. So that's like then basically how like a simple file could look like. And once you're basically done with the whole process of like, okay, I'm fine with like how my schematic looks like now, you then execute a command Atopile while being in that project, and actually goes through all the, like, first of all, it goes through all the assertions. So it basically checks that, like, yes, the power, allowed power voltage of the LED is indeed within 3.5 to 5.5 volts, more specifically 5 volt, and also the data voltage is within what is allowed. If it wouldn't be, then you could get an error here. It shows you like the overview of like what components you have here, what the designator is, which then later on is like relevant for the placement. And you also can see what component actually was like automatically selecting for the capacitor. In this case, it automatically selected this specific one, the specific capacitor, because it was available. And it then created basically the netlist file. And that you then basically just import into KiCad. Actually, that part I forgot to prepare. But shouldn't be a problem. And yeah, so we have like the KiCad files as we're used to, and then we directly go to the layout file. And in this case, just a bunch of LEDs that I already prepared. And now every time I make a change, for example, I added new LEDs or change the connections, all I do is click on import and netlist, and then the file, and then basically everything is updated, and that's it. And then if I would have new components that it would show up here, maybe I should have done that. But that's basically the approach of how it integrates with KiCad. I showed assertions. I showed like the basic simple structure. There are a lot of advantages of this approach. I mean, for one, you actually also work directly in your IDE, so you also have Git directly like accessible and integrated. If I do make a change, it's much easier to remember to actually commit all the changes and describe what have you changed, so that you can go back to like a previous state or something. It doesn't work the way you want it to work. You can use Copilot, as I mentioned, or whatever AI support that you want. You can use the VS Code plugins, which is quite useful, for example, for like to-dos, like mentioning what to-dos you still have to do here. You can use continuous integration, so to automatically, for example, generate the PCB files every time you make a change, or to automatically check for like code issues, basically, which is not really practical with like regular KiCad files because they are not exactly very readable, unlike this code. It also makes the reusability of like modules much easier without accidentally forgetting like a specific part, for example. You just import it. Just like you do with like other code. And also it makes it easier to like design like complex systems in a way that is much easier to understand, because they have like can then separate everything much better into smaller and smaller projects, modules. And to show how that can look like, I'm going to show you a bit of a more complex example. So these RGB LED lamps that I worked on, basically, so I created RGB LED lamps with some acrylic tube and some LED strips in the middle, and some circuit board I designed myself in the base. And it has a bunch of components. It's powered by USB-C power delivery, and it converts power and all that stuff. And so we do have a little bit more imports here. But honestly, I could even like organize this even better. And with the knowledge that I gained while preparing this talk, I actually also know how to like improve the readability even more. But anyway, so like I have this main PCB in this case, and I define basically all the different power sources that I have here. The 5-volt one, the 3.3-volt one, the V-bus that is coming from the USB-C connector directly. I have my interfaces for I2C, I2S, and all that stuff. And I then basically connect them. I say that the power from the microcontroller is connected to 3.3 volts, that it's connected to UART and all that stuff. I can add comments for both having overview of like what I already checked, or what pins I actually use for what kind of purpose. You can be very creative in like how you use the comments, and like in KiCad it's getting quite messy quite easily when you're like integrating comments a lot. I have some buttons here. I have the USB-C connector, and as I mentioned, for example, like the USB-C connector, USB is connected to USB, and then I don't have to remember again like what pins are basically for what purpose. I do it once, and just makes the whole process easier. And like for example, let's see if there's a good example that I can show. We have level shifters, and for example, I have like the USB-C power delivery module, which in this case is based on just the module with all the core components, and then I have like the separate module that has the resistors required to request a certain voltage. I could then also make, for example, another module that requests instead of 9 volts to 20 volts, maybe requests like 20 volts minimum, and I don't know, it just makes the whole reusability part like much easier once you get like a little bit more used to like writing this language. And yeah, what else? We can also define ranges here, which is again also quite useful for like assertions and just generally speaking. Again, this could be even better split up, to be honest. Like with all core projects, like you also have to think about like at what point you want to split it up into more files, and how much is too much for one file. But anyway, so yeah, this was like a bit of a more complex project example. There are also like a bunch more examples from the people from like Atopile and like the community, where they built some like servo motors and other stuff, and they're quite interesting, and using a lot of the assertions, for example, for like implementing the formulas that you have in data sheets. I only tapped slightly into that so far, but like the whole assertions functionality is definitely quite interesting. That said, coding a schematic is not a new idea. However, there are quite some differences in comparison to like the more commonly used project before, which is Skittle. So Skittle is also a language. Well, sorry, it's a project that allows you to create schematics or like netlists that you can then import into KiCad by writing them in code. However, it's based on Python. Like it's not designed specifically from the ground up for describing hardware. So I would definitely argue it's like a lot harder to read and not as intuitive, because you're like using a general purpose language for something it wasn't really optimized for. And yeah, Atopile is specifically designed for that purpose, and keep extending it. Have been like working on adding more and more features over time as well. Also, by the way, in case you were wondering about like, okay, so the whole code overview, useful and so on, but I want to have my visual schematics. They actually also have been working on creating like a visual schematic overview, which it's in progress, and it's definitely, I think, going like in a good direction. And that also then allows you to more easily communicate with other engineers once they fix these placement bugs, basically. And you basically then have like something that looks like a lot more familiar to a regular schematic. And it also makes the communication with engineers who don't want to learn like this coding language quite easier. Since this is like definitely one of the my main critique points about this. Like, it's a really cool project, but it would also be good to be able to have this kind of schematic overview automatically placed that looks like a easy to understand schematic to communicate with other engineers together. And yeah, that's also something, to the best of my knowledge, that Skill doesn't have either. Yeah. So, but honestly, like the true magic, I would say, from like writing schematics in code really comes from making use of large language models in AI specifically. Because like it's a lot easier to ask an AI or like to train an AI on generating code for like a schematic that looks like this versus like how a regular KiCad file looks like, which is not exactly human readable. And so I was playing around a bit with this. Keep in mind that this is some, is it readable? I guess so. Like, this is the worst result you're gonna get going forward. Like, and it already works remarkably well for, especially like for simpler data sheets, for example. So, like, I was playing around here with both Gemini and OpenAI's model. Basically gave it like a long documentation that I summarized or wrote about Atopile, how to use assertions, how generally to use the code structure. And I give it like an example of like, here's a data sheet, in this case for like an LED. Create a schematic file for me. Or like also create like an overview of like the files, the folder structure and stuff like this. And honestly, if one spend more time optimizing like the system prompt and like the documentation, you can get even better results without a different like large language models. But it's already quite interesting of what it can do. It correctly creates like a component, defines the voltage range that is compatible here, connects correctly the pins, even while I would have done it a little bit differently in terms of the structure. But again, that's something that can be fixed by just giving it better examples of like how good code examples look like and how bad code examples would be maybe. And then I have like a module where this LED, like, is connected to power. It has seen the capacitor. It now said, it has a footprint here. And honestly, all that looks really well. I don't see any problems here. And the same with OpenAI. I mean, like giving it some screenshots, and in fact, actually, like OpenAI's model is much better in like following prompts exactly. I also noticed. So like here, for example, it has like the D-out signal, VDD signal, and then also describing what it does. So this is more how I would have done it, to be honest. And yeah, you describe the capacitor and the values and so on. In fact, it follows the commands so good that I actually forgot to specifically mention, like, please do not generate the code for all these other files, which I do not need. Like these totally easily readable KiCad files. Yeah. When it comes to more complex examples, though, this is where it starts to fall currently a little bit more apart. Like, for example, I was like giving it like a 40 pages data sheet from like a text instrument chip, buck converter chip, and it definitely missed a lot of stuff here. Like, it's missing files here. Like, this is again like Gemini. The values here, like the 10K ohm, the 10K ohm resistor is definitely correct, but the 42.2 is at least not what Texas Instruments says in their web interface, where you can actually calculate your specific use case and the specific components that you need for that, like output, for example. Doesn't exactly match up, and I'm definitely going to trust the website from Texas Instruments more in this regards. But it's so interesting to like play around, and again, it shows you the direction of like how this is going, because like the models are just gonna get better. They're gonna get even better with like dealing with like large content sizes. And honestly, you can already get like much better results by just having a different approach of how you trigger those large language models that already exist. Like instead of saying like, hey, create a whole schematic all at once, you could also say like, hey, first create this specific part, which is then gonna have like a much higher chances of being absolutely correct, I noticed. Like I noticed when I asked it to create like a whole schematic, it was definitely making some mistakes with the pins. But when I asked it to actually only create the component for the IC chip for the converter, for example, and nothing else, then it actually was everything correct. So like there's definitely a improvisation you can do also in terms of the workflow. And again, this is going to make the whole process of like evaluating a new component and integrating it into your projects a lot easier. Like I don't plan on using like AI generate code to like create a whole schematic, but I definitely see it happening to create like for specific modules. Quickly check over them, see if they match up with the data sheets in general, and then integrate them. And definitely a very interesting approach. So yeah, that was like about large language models and Atopile. And that's basically all the core things I wanted to show so far. And I'm looking forward to questions of yours.
Yes, thank you very much for your talk. Now let's start with the questions.
Yeah, thank you very much. I have several questions. First of all, have you heard of Circuit Painter?
I have not yet.
Circuit Painter does the other way around. They say we describe the schematic and using Python to place the schematic components and routing inside there, which is quite nice if you like want to have an artistic piece of code or something like artistic schematic, or you have like 300 LEDs and want to place them in a raster, which is really, really good because the routing in there is a hassle and it's always like the same and placing in the same grid. Circuit Painter, really recommend them.
Good to know. Yeah.
The second question was, how does it handle pins with different functionality? For example, like it could be a power output pin or it could be a power input pin, depending on the external components of a piece of IC.
I mean, by default, I mean it just treats them as well, just pins. Like it doesn't really like you can make it check with assertions. I would say basically, like it's not directly implemented, but you can use like assertions to, for example, say like this pin type, like basically creating like a variable called functionality or like type or something equals output or equals input, and then based on that you could then use assertions, for example, to double check that everything is correctly connected basically and not wrongly labeled basically. Does that make sense? Like basically you would implement it using these checks that I was showing earlier, where you can create, like we could, for example, then say, let's try it here, data in type equals input or something like that. And so like if you then have like another, if you then somewhere else basically then use that pin and it's accidentally being overwritten with type output or something that, I know you could, I guess it's like how I would approach it. But honestly, like there's like also this Discord community where you probably want to ask this kind of question. So, and they're quite like active. If they're like more, well, Yeah, so like on the website of Atopile, at the top you have like a link to Discord, and asking the question there, or I can also like forward it. It's like the way to get the best answer, I think. No, but like I would approach it with assertions, basically, and write it yourself.
Yeah. It's not Python, but it looks a lot like Python. Can you talk a little bit about how the language works?
I mean, they've written like a language in their own compiler. I definitely see some similarities with Python as well, but it's like their own language with their own compiler, which gives them also like a lot more flexibility because they don't have the restrictions of like how Python code is built up. Yeah, I mean, like the whole idea is really to describe like what the circuit is supposed to do instead of trying to, or complicatedly think how we can reproduce the functionality in Python code or something. It's
Are there higher level constructs like loops?
So they have thought about if statements and loops. There have been reasons why they haven't implemented it so far yet because they were causing a bunch of complications and problems. I also would, like, from my perspective, it also makes a lot of sense to integrate this. Like especially for like the example with the LEDs. Like it's nice if you can use AI to like say like please make it 200 lines, but ideally you just have a for loop. Not implemented yet, but because there was some technical reason why they haven't decided to do it. But it's a good point. I'm definitely going to ask also about this again in the chat, because I'm also would be interested in that.
I have a question. Is it how is the, I would say, library support? Is there a lot of libraries for obscure modules and so on where everything is defined already? Like if you want to have some power delivery, as you showed before, how is the state here? Do you have to write a lot of your own, or is most of it available already?
Good point. Reminds me, I kind of like skipped over some important part here. So two things. For one, they like the approach that I've been using the most is because I've been working also with like LCSC and GLC PCB. Like you have this database from GLC PCB, like the components database, and there all these parts have like their own ID, and you could then decide to simply import them. You can basically install a component directly from GLC PCB, and it creates then like the schematic file for the specific component. For example, for like the LED, like the base of this was automatically generated by using the atto install command. But they also do have, or like used to have at least at the beginning, their own packages, page. So they still have this page here, packages at Atopile, where people have been like sharing existing projects basically, or like modules, and then you can use the install command to install them. And the idea is really to make it similar like to Python packages that you just use atto install. They temporarily deactivated the submission for new components. I think they were like want to figure out basically how to improve this kind of workflow and like the findability of components. But yeah, it's like definitely one of the advantages also of like having this code approach for sure.
Thanks for the talk. One question that came up in my mind is when we are talking about building schematics in code, what's been kind of missing for me is really placing all the calculations you have to do in your code. Like at some point, I think in the power delivery module, I saw something like calculated for 5 volts, the feedback voltage divider, or something like that. And I think, well, if I have to do all the calculations outside of my code and have to put them in manually, then I'm kind of missing the benefits I could actually have if I can just say I have a voltage regulator and I feed in, let's say, 12 volts, want out 5 volts, and Atopile would go ahead and calculate all the voltage divider resistance values that I would actually need for my use case. Is there anything about that in the future, or does Atopile already support that?
I'm not sure if I fully understand the questions. The question, like, are you?
So basically, the most easy use case I think is I have a voltage divider, and I just want to define the ratio of the two output voltages, and could Atopile then automatically pick the correct resistance values for me?
So that's the idea. You do have this whole generics package that basically always comes when you create a new project, an Atopile project. And you do have a bunch of components, including a voltage divider, for example. And yeah, I mean, yeah, exactly. I mean, I think it actually does already what you specifically asked for it. Like, you basically have like assertions to make sure that with the, like, basically have like an input voltage that you define here and an output voltage and like a how do you say it again? Quiescent current. Anyway, it's using the assertions. And like the package, like the resistor packages that are defined here, it should automatically already then search for the correct resistor values that you need. I must admit, personally, in my projects, I have been, because I started working on this like with Atopile before they implemented assertions. At first, I was like always just manually searching for components. And later on, like just started basically using assertions more in the automatic selection. But yes, my understanding is that it already works. Like, you have like this voltage divider component, and then you define your requirements, and then it automatically is searching for everything else. And the idea is to extend this to more and more components. So like currently works for with resistors and capacitors as automatic search. The idea is to also make it work with inductors. Even while that's going to be a bit more tricky because you have like the different footprints and like sizes. But yeah, that is already the case. And there are some more complex examples also on how you can basically use the assertions to automatically find the right components. I can't quickly find that example, maybe later. Yeah.
Yeah, but you answered my question, so thank you very much.
Thanks for the interesting talk. Another question about the assertions. Can you handle more complex things with it, like dependencies? So, for example, if you have to have supply voltage to get a certain clock frequency.
I mean, you can like use variables and like references to variables. I'm not sure like if this goes in the direction of like what you're referring to, or can you?
Yeah, we can see on the slide here a calculation, but more in the sense of if then else.
Okay. If this then or if then else. Again, like if statements are currently not integrated. Yeah. I guess the answer is not yet. Yeah. I think that's the answer, basically. But I'm definitely going to push also for the whole topic of like if statements and for loops, because I also do think that if it doesn't cause really huge issues with suddenly the whole code and compiler breaking or something, it does make intuitive sense to have if statements and loops. Even while I think like one of the arguments was that they are worried that this actually makes the code less readable or something. But yeah.
Any further questions? We've got another 15 minutes, so your chance to ask.
Ask me everything. And also show specific things if you're interested.
Hi. Thanks for the great talk. I have a short question. Do you know of any approaches where this is integrated with auto routing. So my idea is basically to make the entry into this whole thing a lot easier. People just write some code, and on the other end, you get out a PCB where you don't have to think at placing things at all. So, is there any work in this area, or?
I mean, I guess you could combine it, but like it's currently not done. And like honestly, when I started PCB design, I also saw like, oh, like there's this auto routing functionality in KiCad. Amazing, let me use it. Yeah, no. It's like for very very simple circuits, I guess it can work okay. But like as soon as you just have a little bit more complexity, it just quickly cannot find connections where you yourself can definitely find connections between like components. And it's like the auto routing functionalities that I've seen so far, at least. Doesn't mean that those are all the ones that exist. They just don't have enough knowledge of like your requirements. They don't know basically enough about the components and what is important here and like the requirements from the data sheets to make some really good calculations. If they would have all this information from the data sheets, I could definitely imagine that auto routing working a lot better, but like, yeah, not the case currently. But I mean, the nice thing is also that because like it's a code like project effectively, you can also automate a lot of stuff yourself, and you can do the continuous integration stuff. And so even if functionalities and connection to other software doesn't exist yet, you can make it work if you want to, or you can experiment with it at least.
Any further questions?
One more here, I think.
So I've never done PCB design, so I literally have no idea. I'm just sitting here and like looking at PCB design because I did electronics, but never actually designed a PCB. So you've mentioned that there's already a software which uses Python to do things. And you specifically complained that that's not a good idea. So I'm curious, could you elaborate a bit on why it isn't a good idea? For example, an argument for Python right now would be, well, Python already has for loops and if statements.
Yeah, so while researching like for the talk, honestly, was the first time I was stumbling over like Skittle, and I did try to understand better like the differences. The main thing that I clearly notice is it's just written in a quite different way, and isn't exactly easy to read, I would argue. Like what is like destination template even here, for example? This is, by the way, the example they take, like the default example in Skittle from like the Git repo. And it's just like if only can judge so far like the readability aspect of it. I did remember that like I also asked the question like in the Discord, like, so can you explain again like what the core differences are between like Skittle and Atopile? I think the reasoning was something like that like Atopile basically describes what the circuit does, and basically Skittle how it's like built up. I'm not sure if that makes that much sense, but I would have to do more research, to be honest, and like I tried out more in practice to like say more about even more about like the differences. But the thing that I noticed is just like the readability is like worse, and like you're just more limited by working with something that wasn't designed for that purpose. It's a little bit like you can do CAD in Blender, like CAD modeling. It doesn't mean it's a good idea. Like there's like CAD software specifically designed for CAD 3D modeling that just works a lot better instead of like using a software that was designed for something else and try to adapt it to that purpose. Yeah.
Any other questions?
Here at the front.
How are the footprints handled? Are they defined in KiCad classically, or is there a new approach to also define them in code?
So when you like if, for example, you install like a part from JLC PCB as an example, it would automatically, first of all, generate this Atopile with like basically the pins and how they're connected. It would then also download the footprint file and download it into the footprints folder. And there you just have your regular KiCad footprint file. So currently it's like optimized for this whole KiCad workflow. But they could also extend this in the future to like other software like Altium, for example. But like, yeah, they're basically being downloaded. Or what you can also do is if you create your own part in KiCad, in the footprint manager, you can then basically export it, save it as a file, and then just basically give it the name here, like say like what file name it has, and then automatically we'll match that together. So yeah, option 1, basically download it, install it from JLC PCB. Or option 2, create your own footprint in KiCad, and then export it there. Yeah.
Any more questions? All right. Then thank you very much for this little introduction into modern PCB design. Please give it up for Kitty.